Transverse and longitudinal wave. This is our next topic in the chapter wave, and hence our video number 2 on this topic of waves. Transverse and longitudinal wave, you would have heard about these terms in your previous school life. In this lesson here, we'll understand the technical details about these waves, which is, believe me, not difficult at all. So let us quickly review and recall how these waves look like. So a transverse wave looks something like this, as in picture 1. So what are you doing? You are taking a slinky spring and you are trying to produce both the transverse and the longitudinal kind of wave on this slinky spring. Picture 2. Picture 1 and picture 2. Picture 1 is your transverse wave. Picture 2 is your longitudinal wave. If you look at how you are moving your hands in picture 1. In picture 1, you are moving your hands side to side. As a result, the waves which are produced are also kind of side to side, right? Side to side, which is a kind of a transverse wave. Alright. Whereas in picture 2, if you see, how are you moving your hands? You're moving your hands backward and forward on the slinky spring. As a result, the disturbances that you see here, they are also kind of backward and forward at every point on the slinky spring. These are known as your longitudinal wave. Longitudinal wave will have a series of high density regions. Can you see high density coils? High density coils of the slinky spring. By coils, I mean the coils or the turns of the slinky spring. The region where you have high density coils, they are called your compressions. The region where you have low density coils, they are called your rarefaction. Alright. Whereas in the transverse wave, you have a series of crest and troughs. Crest, as we all have understood in the previous chapter, this is your crest. The topmost point of the wave is called the crest. The bottommost point is called the trough. Right? And in the longitudinal wave, what do you have? You have alternate compressions and rarefactions. You have a compression. Let me write compression, rarefaction, compression, rarefaction, compression, rarefaction. And in a transverse wave, which would look something like this, you will have alternate crest, trough, crest, trough, crest, trough, so on and so forth. So crest and troughs are similar to your compressions and rarefactions. Alright. So transverse and longitudinal wave, we have understood the basic look of them. Let us understand some technical details about them now. So here again on the screen, if you see a transverse wave produced in the picture 1. You have a transverse wave in a rope. You have a transverse wave in a rope. The rope is tied at one end to a point on the wall, and you're moving the other end up and down. The up and down motion of the rope we'll understand this text. Just hold on for a bit. Right, so you're moving your hands up and down, the wave is produced. In which direction is the wave moving? Look at this arrow. The wave is moving from left to right. The wave is traveling from left to right. So the arrow here tells you that the wave is moving from left to right. Let us look at the second picture now. Here we are talking about a longitudinal wave in a spring. So here again you have a spring, a similar situation as compared to the previous picture. The spring is also attached at one end to a wall. How are you moving your hands? You are moving your hands backward and forward along the line of the slinky. So you're moving your hands. That's the arrow, the blue arrows. If you pay attention, blue arrows depict how you're moving your hands. You're moving your hands backward and forward in the same direction as the as the length of this slinky spring. How are these compressions and rarefractions moving? They are moving left to right. Here also, if you see, the direction of the wave is left to right. Compare these two important points. How is the wave traveling in both the pictures? Left to right. Here as well, the wave is moving left to right. So before we understand what is a transverse wave and what is a longitudinal wave, it is important that we understand these two phrases. So what I have written here, important phrases to understand. Important phrases to understand. Phrase 1 and phrase 2. So let us start with phrase 2 because we have understood it slightly already. Phrase 2 is the direction of the travel of the wave. So if you see in picture 1, the wave is starting from your hand and it is moving all the way towards the wall. That's the direction of the travel of the wave. So this is your phrase. This is the meaning of your phrase 2. So when we talk about phrase 2, what does it mean? We mean this and this, which I am putting a tick mark on. The direction of the travel of the wave. What is a phrase first of all? Phrase is an English term which means a group of words which come together and they have a meaning, right? So the group of words that we are talking about, the direction of the travel of the wave. This is a scientific phrase that you should remember and you should understand its meaning. The direction of the travel of the wave, how the wave is produced, from which point the wave is produced and to where it is moving. This is your direction of the travel of the wave. Direction of the travel of the wave. In the first picture, the wave is produced by your hands, which is moving up and down. As a result, zigzag motions are traveling all the way towards the ball. The direction of the travel of the wave is left to right. In picture 2, also the wave is produced by your hands and the disturbances ultimately are moving towards the wall. So direction of the travel of the wave is the direction in which the wave disturbances are traveling, right? Let us understand the second phrase now. Second phrase, the oscillation of the medium. Oscillation of the medium. So let us focus on the first picture. What is the medium which is oscillating here? What is the medium? It is the rope. In the first picture, the medium is your rope. It is the rope which is oscillating, right? Take any point on the rope. Let us put a mark. You can take a red pen and you can put a mark, or you can tie a red ribbon on the rope. Produce this transverse wave on the rope. How is this red ribbon mark moving? You can tie a red ribbon or you can take a red pen and put a mark, right? A big mark on the rope. How is this red mark moving? You'll see that red mark is moving up and down. This red mark will be moving up and down. Similarly, you take a red ribbon and tie it anywhere on this spring. How will this red ribbon mark will be moving on the spring? It will be moving backward and forward. It will be moving to and fro. As the compressions and rarefraction pass through this set of coils, this red ribbon will be moving like this, to and fro, right? So that's called the oscillation. Here, any particular molecule or any particular mark on the rope is moving up and down, which is a transverse wave. And whereas in a longitudinal wave, any particular point on the transverse wave is moving backward and forward. Backward and forward. Now compare the phrase 1 and the phrase 2. Right? Let me just remove the extra bit of things from the screen. Compare compare the oscillation of the medium. We'll move step by step. We'll start from picture 1. Compare the oscillation of the medium with the direction of the travel of the wave. So you have to compare what? You have to compare the oscillation of the medium, which is this arrow, and the direction of the travel of the wave. What is the angle between them? The angle between them is 90 degrees. If you see, they are at 90 degrees. They are perpendicular to each other. Is it making sense? Now let us look at the picture 2, which is a longitudinal wave. In picture number 2, if you compare the oscillation, compare the phrase 1, the oscillation of the medium with the direction of the travel of the wave. They are parallel. What do you see? This line and this line. They are parallel. Here they are parallel. That's the difference between a longitudinal wave. You need to understand these scientific phrases. Phrase 1, which is oscillation of the medium. You have to say it several times in your mind and understand what it means. Oscillation of the medium means any particular point on that medium. It can be a rope, it can be a spring. Any particular point. How is it oscillating? Think about it. Phrase 2. The direction of the travel of the wave. How is the wave energy moving? Compare them. If they are perpendicular, if the oscillation of the medium is perpendicular to the direction of the travel of the wave, if the oscillation of the medium is perpendicular to the direction of the travel of the wave, it is your transverse wave. Whereas if the oscillation of the medium is parallel to the direction of the travel of the wave, compare these two lines, oscillation of the medium and the direction of the travel of the medium and the direction of the travel of the wave, they are parallel, then this is your longitudinal wave. It is very important that you understand these definitions because it's an exam kind of question. So let us move on to understand each of them separately now. So you know the two phrases. How do you define transverse wave? In a transverse wave, the oscillation of the medium are at right angle to the direction of the travel of the wave. You're combining phrase 1. Let me use a contrast color. You're combining your phrase 1 and you're combining your phrase 2. P1 and P2, you're combining with the term right angle here. So this is your transverse wave. You need to understand, or you need to repeatedly saying these words in your mind so that you understand the scientific meaning of them. So what is a transverse wave? I am at the bottom of the screen. The oscillation of the medium, which is phrase 1, connected with the term right angle with the phrase 2. When the phrase 1 is connected with the term right angle with the phrase 2, it is a transverse wave. The oscillation of the medium is at right angle to the direction of the travel of the wave. How is your hand moving? How is your hand moving? Up and down. Similarly, any other molecule on the wave would be moving up and down. It is at 90 degrees to the direction of the wave travel. So this is your transverse wave. The connector term between phrase 1 and phrase 2 is right angle. The connecting term is 90 degrees or right angle, so it is a transverse wave. Both transverse wave and longitudinal wave are defined in the same manner. Only thing, for transverse wave it is the right angle term that you use. For longitudinal wave it is the parallel term that you use. Alright. So the examples of transverse wave: light around us is a transverse wave. Microwaves are transverse wave, ultraviolet wave, the microwaves, sorry I wrote microwave 2 times, infrared waves, radio waves, X-ray, gamma rays, everything, all these waves, most of the waves around us are actually transverse wave, right? Similarly, now that you have understood longitudinal wave, you'll find it easy to remember and recall and write in your answers the definition for longitudinal wave. Longitudinal waves are the oscillation of the medium is parallel to the direction of the travel of the wave. Same set of lines you are using, the only term which gets changed is parallel. Now you are using the term parallel here. Phrase 1 and phrase 2 are connected by the term parallel. Oscillation of the medium, how is your hand moving? To and fro. Similarly, any other point, any other point on this spring will be moving backward and forward, and it is parallel to the direction of the travel. Parallel. The connecting word between phrase 1 and phrase 2 has now changed to parallel, so it means we are talking about longitudinal wave. Example of longitudinal wave, the sound wave is a longitudinal wave. Let us understand why sound wave is a longitudinal wave through this picture. Sound waves are longitudinal waves. Why? Because when you speak, compressions and rarefaction travel out through the air. So when you are speaking, the vocal cord is vibrating inside your throat, which is producing compressions and rarefaction. Suppose that you have this loudspeaker. So what is happening? The loudspeaker is making sound waves. The front end of the loudspeaker, which is made up of usually a soft cloth, it vibrates. It moves out, it moves in, right? It vibrates like this. It vibrates with different amplitude. So as it moves out, as it has come out, it has pushed the air molecules here closer together, which is producing a compression. This compression starts now moving in this direction. Alright, say that next this front diaphragm, it has moved inside. Now it has moved inside like this. Now there is a lot of space, so as a result the air molecules are far apart. This creates a rarefaction. So rarefaction now follows the compression. So therefore, when the diaphragm moves outside, it pushes the air molecules together, it produces a compression, and this compression starts moving forward. If the diaphragm moves inside, there will be a lot of empty space created, air molecules spread out, it creates a rarefaction, and this rarefaction which is created, it does not stay there, it does not stick there, but this rarefaction starts moving ahead. So that's how a series of rarefaction, compression, they follow each other in a pattern and they start moving away for the diaphragm, and that's how the sound travels from one place, from one location to another location. So I've given you a brief about how the sound waves work, how the sound waves travel. Sound waves are longitudinal waves. Alright, in the next topic we'll be talking about waves and wave fronts. It is very important.